Welcome to the online lecture series of heat and mass transfer. Here is Professor Lakshman Mane. This is a video session on electrical analogy and thermal resistance in plane wall, hollow cylinder and hollow sphere. In this session, you will be able to explain electrical analogy, thermal resistance in plane wall, hollow cylinder, hollow sphere and in convection. Let us know about electrical analogy. In practice, we come across a number of composite structures through which heat transfer takes place. For example, wall of boiler house, insulated steam pipe. Also, when heat transfer takes place by conduction, convection and radiation, the solution becomes difficult. So, the heat flow calculation in such cases can be worked out easily using a technique known as electrical analogy. When two or more physical processes are expressed by using same formula, then they are said to be analogous to each other. Here we can see analogy between electrical and thermal system. So here these are the parameters for electrical and these are parameters for thermal. In that, heat transfer by conduction process. So here we see energy that flow in electrical is electrons and in thermal is energy. Rate of flow is in electrical as a current, means I. In thermal it is considered as heat transfer, that is a Q, means heat transfer rate in watt. Driving force for taking flow is in electrical is a potential difference, means in a volt, delta E. In thermal it is a temperature difference, that is delta T in degrees Celsius or Kelvin. Governing factors are here in electrical resistivity, that is ρ. Its analogous factor in thermal is thermal conductivity in K. Cross-sectional area of conductor is taken here as A, where in thermal system it is taken as a area normal to heat flow. In electrical, length of conductor is taken as L, while in thermal system it is considered as dimension of object along the heat flow. It is denoted by letter B. In electrical system, electrical resistance R is considered. Its analogous parameter in thermal is thermal resistance, means RTH. In electrical system, electrical resistance is a function of resistivity, cross-sectional area and length of conductor. In thermal system, thermal resistance is a function of thermal conductivity, area and dimension of object along the heat flow. We will see here Ohm's law. By the law, flow of current varies in proportion with potential difference. So it is written as I is changing in proportional with change in potential difference. With equality sign we can write I is equal to delta E by R, where R is electrical resistance. Analogous term or analogous formula to this we can write by the analogy between electrical and thermal system, as already discussed. Here I is analogous with Q, means heat transfer, delta E is analogous with delta T and R is analogous with RTH, So heat transfer can be written as Q is equal to delta T upon thermal resistance. So for electrical system, these are the parameters. I is a flow of current, delta E is a potential difference, and R is electrical resistance. For thermal system, these are the parameters. Q is a rate of flow, delta T is a temperature difference, and RTH is a thermal resistance. This is electrical circuit. We can see this is a current flowing through this circuit. This is the potential difference between the two points or voltage difference E2 minus E1. This is a resistance in the circuit R. Analogous diagram to the electrical circuit is thermal circuit. Here you can see in this diagram, here the respective analogous parameters are written. So here analogous to delta E, here is temperature difference delta T. Analogous to current, here is a heat transfer Q. And analogous term to electrical resistance, here is thermal resistance RTH. Now we will see thermal resistance in a plane wall. This is a simple structure through which heat transfer is taking place. So here you can see this is a T1 temperature, this is T2 temperature, this is area, this is thermal conductivity, and this is dimension. Now according to the Fourier's law, the heat flow means heat transfer through the plane wall is Q is equal to K into A into T1 minus T2 divided by B. So T1 minus T2 is delta T divided by B is a distance. So delta T by B means temperature gradient. So Fourier's law is what? Q is equal to thermal conductivity into area into temperature gradient. Now here in this case Q is equal to Ka by B into temperature difference. Rearranging the term, we get this formula as a Q is equal to delta T divided by this term B divided by K into A. Now compare this expression with this thermal resistance equation, that is Q is equal to delta T upon RTH. So in this equation, here you see left side is the same. In a right side, numerator is also same. Means here we can have this denominator RTH is equal to this expression B by Ka. So in this way we can have thermal resistance for plane wall or infinite slab, that is B by Ka, where B is a dimension, K is a thermal conductivity, and A is a area perpendicular to direction of heat transfer. Similarly, we can have thermal resistance in hollow cylinder. Here we see this is a hollow cylinder. So heat transfer is taking place from inside to outside, from temperature T1 to T2. Inner cylinder radius is R1, outer cylinder radius is R2. So according to Fourier's equation, the heat flow through the hollow cylinder is given here as a Q is equal to 2 pi Lk into T1 minus T2 divided by natural log of ratio of radius R2 to R1. Here L is a length of infinite hollow cylinder, K is the thermal conductivity, and these parameters already shown in diagram. So arranging this equation in this form, 2 pi Lk delta T by Ln R2 by Rk. So here rearranging the terms, here we get Q is equal to delta T divided by this expression, that is natural log of R2 by R1 divided by 2 pi Lk. Now similar to earlier case of plane wall, here also we compare this equation with this analogy equation, that is Q is equal to delta T upon RTH. Comparing these both equations, we can find here similarity in Q and dt. So here thermal resistance for hollow cylinder will be what? This denominator quantity RTH is equal to natural log of R2 by R1 divided by 2 pi Lk. Now we will see thermal resistance in hollow sphere. So here in this image we can see a sphere cut section, inner radius R1 or outer radius R2. Temperature inside T1, outside T2, heat transfer flow direction. Now according to Fourier's equation, the heat flow means heat transfer through hollow sphere is given as Q is equal to 4 pi K R1 R2 into T1 minus T2 divided by R2 minus R1. So this T1 minus T2 is temperature difference, K is the thermal conductivity, R1 R2 are the radii. Rearranging the terms, we get Q is equal to delta T divided by R2 minus R1 divided by 4 pi K R1 R2. Comparing this with the Q is equal to equation delta T by RTH. So from these both equations, we find thermal resistance for hollow sphere means RTH is equal to this quantity means expression R2 minus R1 divided by 4 pi K R1 R2. Now this is a thermal resistance in convection. We know that convection is a process of heat transfer in which heat flows between surface and the fluid surrounding it. So heat flow rate by convection is given by Newton's law of cooling, that is Q means heat transfer flow rate is equal to H into A into bracket Ts minus Tf, where Q is a rate of heat flow in watt, H is a convection heat transfer coefficient, its unit is watt per meter square Kelvin. A is the surface area in meter square along which the fluid is flowing. Ts is average temperature of surface and Tf is average temperature of surrounding fluid. Now this is a diagram. Here you see this is a fluid flow which is passing over this surface. This is the heat transfer across the surface is taking place. Here temperature of Ts is shown, the temperature of surface, Tf is the temperature of fluid, and here temperature of surface is greater than temperature of free stream means fluid which is flowing above the surface. Now for this case, here rearranging the equation, we get Q is equal to delta T means Ts minus Tf divided by 1 upon HA. Comparing this with Q is equal to delta T by RTH, here you can have numerator and denominator. So numerator is the same for both. So denominator we can have here equating the denominator. RTH means convective thermal resistance is equal to 1 upon HA. Here for the betterment of concept, here this is a diagram for thermal system. This is a heat transfer flow from the surface to the surrounding fluid at Tf. Convective heat transfer coefficient is H. Here this is electrical circuit. This is a heat flow between the two temperatures means temperature difference Ts minus Tf, and this is a convective thermal resistance RTH is equal to 1 upon HE. So in this way, at the end of this session, you can explain electrical analogy, thermal resistance in plane wall, in hollow cylinder, in hollow sphere, and in convection heat transfer. If you like this video, please subscribe and share. Thank you.